Okay, in this video we're going to look at the effect of temperature on the rate of reaction. Temperature is going to affect the rate of reaction in both of these ways. So remember what we're talking about here. To have a successful reaction, we have to have a collision between the required reactants in some sort of combination that will allow them to form the products. And when they have that collision, they have to have enough energy to overcome the activated complex to provide the activation energy and allow them to transition from being the reactants to being the products. To talk about this, we need to slow down a second and make sure we have a really good understanding of what temperature really means. Temperature is a measure of the average speed of the particles in a substance. But Maxwell Boltzmann came up with a way to relate this temperature not just to the average speed of the particles, but also to the distribution that shows what speed most of the particles in a substance will have at different temperatures. So that's what this graph here is. This is called a Maxwell-Boltzmann distribution. And let me label the axes here. The x-axis is the speed of the individual particles, or we can think of that as the kinetic energy. The faster the particles are going, the higher kinetic energy they have, and the more likely they are to have enough energy to engage in the chemical reaction to form the activated complex. On this side, we have probability. So for this graph, this is the most common speed for particles, somewhere about 400 meters per second. On this graph, this is the most common speed of particles, somewhere around 750 meters per second. But we can see that not all of the particles at 300 degrees Kelvin or 27 degrees Celsius have the same speed or the same energy. Some of them are going faster, these guys up here, and some of them are going slower. What we can see is as you get faster and faster and faster, the likelihood of particles having that speed gets lower and lower and lower. Similarly, at 1,000 degrees Kelvin, or 800 or so degrees Celsius, the particles tend to have more speed than they did at 300 degrees Kelvin. We can see that the graph is shifted to the right. What that means then is that there's a higher probability of those particles having higher speeds. Not every particle would be moving faster, but in general, or on average, they're moving faster. And we also notice that the distribution widens up quite a bit. With faster speeds, two things happen. One, I think the simple one, we get more collisions. There's no trick here. If we imagine some bouncy balls in an enclosed cube and we make them bounce, if we make them bounce faster, they're going to run into each other more often than if we make them bounce slower. So the fact that things that are going faster run into each other, I don't think needs a lot of explanation. Faster particles, more collisions. But the secondary issue, if we imagine if these particles have enough energy to engage in the chemical reaction when they collide, is also affected by temperature. The faster they are, the more likely they are to have the energy required for the reaction to occur. Let's imagine that we are dealing with some specific reaction that has an activation energy associated with about 900 meters per second. Or if the particles are going as fast as 900 meters per second, they'll have enough energy to engage in the chemical reaction. So I can put an imaginary line up here. And every particle to the right of this line would have the speed required for the chemical reaction. Now let's get some color here. At the cold temperature, I'll use blue, we could see that only these little particles right here would have enough energy for the chemical reaction. If we look at that, we might say that that represents maybe about 3% of the overall particles, which means that for every 100 collisions that occurred, maybe 3 of them would have enough energy to engage in the chemical reaction. Alternatively, if we were able to take this substance and heat it up to 1,000 degrees, then all of these particles would have enough energy to engage in that chemical reaction. This is something more like 40% of our overall particles. That means not only are we having more collisions, but if we had 100 collisions, at the low temperature, approximately 3 of them would be successful. And at the higher temperature, approximately 40 of them would be successful. So faster particles, more collisions, but also faster particles, more energy available in collisions. Means more effective collisions. So that is 2 ways in which increasing the temperature will increase the rate of reaction that we would observe for a chemical reaction.